Hello everyone. So today I'm going to explain how the Leiden algorithm works. That is an adaptation from the Louvain algorithm and is way faster, and I'm going to explain how it gets faster when you use this algorithm. So it's based on the original article that from Louvain to Leiden guaranteeing well-connected communities. So this article explains how the algorithm works and shows some issues that we had in Louvain algorithm that the Leiden is trying to solve it. Let's begin with the network graph. So this algorithm is basically for detecting communities inside the graphs. So beyond he says the number of communities, it says which members is in each community. So to begin, let's start with a simple graph to explain better. And this graph, it's made out of nodes and links between those nodes that has some weights in those links. For example, we have this little graph here that is from 0 to 4 or 5 nodes. And between those nodes, we have some connections, and those connections are weighted. So, for example, between 1 and 0, we have a connection with the weight of 4. And between 1 and 2, the connection has a weight of 1. So the algorithm starts assuming that all the nodes has its own community. So the node 0 is inside the community 0, the node 1 is inside the community 1, and so on. And to begin the algorithm, we have to set a random execution queue. For this reason, we have to set a random state in the Leiden algorithm. So this queue, for example, let's say that we begin with 2, 0, 1, 3, and 4 to start the calculations. The main objective of this algorithm is to optimize the modularity function. So what is the modularity function? Is this function that basically says how well connected to a community is comparing to another community. So if we have a higher value of modularity compared to another community, it says that this community is more well connected than the other community. So the function basically is this one that you can see in screen that just center here. And it's basically 1 divided by 2 times m. So this m is the sum of all the weights of the connections here. The sum, the 2 4, 3 1s, and 2 2s, we have to sum this to get the m value that is applied in every calculation that you're going to do. This aij is the weight between two nodes. The ki and kj is the sum of all the connections of that node. For example, if we evaluate the 2 and 0, for example, 2 is going to be, the k for 2 is going to be 1 plus 1 plus 2 because, and plus 4 because its neighbors are those. And for 0, for example, we have 4 and 1. The sum of 4 plus 1 is going to be the k value in this formula. So it's the same aim here. And this last term here is just to say that it's 1 if those nodes are in the same community and 0 if they are in the different community. So we use this just to say that we calculate just for nodes that are inside the same community, right? So if they're apart other communities, it does not make sense that we calculate that. So let's begin the algorithm once we explain this function. We know that the m is for every calculation that we are going to do. So let's calculate the m that is going to be the sum of all the weights. In this case, we have 4 plus 4 plus 1 plus 1 plus 1 plus 2 plus 2. And it's equals to 15. So we have the value of m, and now we are going to calculate all the modularity for all assumptions that we are going to do here. So basically, we are going to move those nodes inside the community of the neighbors. So once move to community 0, and then to community 2, community 3, and we calculate how the modularity is in those movements. So the higher the modularity we get from that movement, so you assume that this modularity, this new community is the one that's going to take place. For example, first, as I said, we set the random execution queue, and the 2 was selected to be the first one to be evaluated. So we know that 2 belongs to community 2, And we have its neighbors, community 1, community 0, and community 3 and 4, right? So let's do the first movement that is going to happen, the 2 moving to community 0. So if we do this, 2 moving to community 0, so let's see all the values that you're going to apply to the modularity function. So the m is 15, and the aij is the connection between 2 and 0, that in this case is 1, right? The k2 is all the sum that the nodes connected to 2 are related to. For example, in this case, we have 1 plus 1 plus 4 plus 2. We have 1 plus 1 plus 4 plus 2 is equal to 8. So the k0 is the same thing, but for 0, the node 0, 4 plus 1. So we have here the number 5. We have all the values for that equation. The modularity for 2 and 0 is going to be 1 divided by 2 times 15, that is the m, multiplied by 1 minus, that 1 is the a20, minus 8 times 5, that is the k. For 2 is 8, the k for 0 is 5, divided by 2 times 15. So this value came up to be minus 0.011. This is the modularity for moving 2 to community 0. This negative number means that if 2 stays in the same community, we have this better value of modularity instead of moving 2 to 0, because we have a negative number, and the nodes when are alone in their communities has a modularity of 0, right? Because if you do all the calculation, you're going to get the 0 value. So making this movement is going to be worse than let the 2 alone in its community. So let's move on. Let's go on to see what happens if we move to the other communities. For example, 2 moving to community 1. So we have the same m value, that is 15. We have 2 connected to 1 has a weight of 1, if you can see here, right? We have the k2 equals to 8 that we already calculated here before. We have the k1 that is the sum of those weights, 1 plus 1 plus 4, that is 6. We calculate the modularity, we have the value of minus 0.020, like in the similar situation that happened before with 2 and 0. So let's move on to moving to community 3, and it has a value of 0.022, so it's a better result moving 2 to community 3. And if we do 2 moving to community 4, and we calculate the A to 4 the same way, and we calculate the modularity, we have the value of 0.08. So this value is bigger than other ones. So for this first step, it's better that 2 moves to community 4 than every other community, or 2 stays alone. As I said, if 2 stays alone, the value of modularity is 0. So this movement has a value bigger than the 0. So we have the 0.08 here, right? So moving this, making this movement, so we have here the next situation that we have 2 moving to community 4, and we have those alignments here, and going to the next node of the line, the 0, and we have to see where 0 is. 0 is here, and the movement that 0 is going to do is going to community 1, or going to community 4, or going just those 2 options, right? So let's make this calculation. So first of all, we get this line, so we get to here community 0 going to community 1. So if we make this movement, we have Vm, that's 15, A0 to 1 is 4, right? K1 is 6, K0 is 5. And the function of modularity, we have the value of 0.1. This movement is better than 0, is bigger than 0, so it's a good movement, right? But let's calculate the movement from 0 to community 4. So this one is kind of different, because we have two nodes inside the community 4. So what do we have to do? We have to calculate the modularity for 0 and 2, then 0 and 4, then 2 and 4, and sum all the modularities. So we have 0 to like minus 0.01, 0 and 4 minus 0.003, and 2, 4, 0.08. When we sum all of them, we have the value 0.036. So if we move 0 to community 4, we have the value of modularity of 0.36. And as we are comparing moving 0 to community 1 or community 4, we have a bigger value for modularity. In this case, moving 0 to community 1, right, is 0.1. So this movement is the one that we are going to take. And we have an observation here, note, that says that when we move 0 to community 1, we affect its neighbor 2, because neighbor 2 previously were connected to community 0, and now it will lose this community, will change his connection to community 1. So once it happens, the 2 must be calculated again, so we come back to the end of the line here, right? As it says here, neighbors affected by this change at 0 to 1, must return to the end of the line. So in this case, let's return to the end of the line, right? And let's go to the next movement. So as we finish up this movement, we have the new, that's the one that we had before, and the new community is going to be this set. Like community 1 now has 1 and 0. The community 0 is extinct, does not exist anymore. Community 4 with 2 and 4, and community 3 with the node 3. So let's go to the next calculation, next evaluation. That is node 1, I believe so. I did with node 2, node 0, node 1 now. But in this next configuration, node 1 has its neighbor community 4 and community 3, and is inside the community 0. So we have the modularity here for node 1 belonging to community 0 with node 1 belonging to community 1 with 0. And we have the modularity value for this community, and we will compare the modularity value that we move node 1 to community 4, node 1 to community 3, right? So if we see here, first movement moving node 1 to community 4, right? As we said before, the calculation we must do with all the nodes like 1, 2, 1, 4, 2, and 4, and sum all the values of modularity to get the net modularity in this case. And as we move 1 to community 4, we have a total modularity of 0.02. Remember, the previous modularity, the 0 to 1, was 0.1, right? So it is still bigger than 0.002. And let's do the next movement from 1 to 3. When we calculate the modularity, we have a modularity value of 0. So 0.02 and 0 is less than 0.1 that we had before. So this movement does not occur, and the community stays the same. As we had this one, we go to this one, that is the same one. And going back to the line after the node 1 evaluation is the node 3 evaluation. So if we go back to the community that we had going to evaluate the node 3, and this movement must be to its neighbors to community 4 or community 1. So going from community 3 to community 1, we have this modularity value. So doing all the calculations, 1, 3, 0, 3, 0, 1, and 3, 1, 0, the sum of the modularity in every case, we have 0.02. So remember, node 3 alone in its community has a modularity value of 0. So if you have any value bigger than 0, it's going to be a better movement to do with this node to this community. So we have 0.072 here in this case. But we still need to continue evaluating the movement of node 3 to other communities. So node 3 to community 4, we have these values. So we got a sum of 0.136 that is bigger than 0.072. So this movement has a better quality of community by the modularity function. And this movement, if you see the network here, if you change node 3 to community 4, node 1 that before had a connection to community 3 will not have this connection anymore. All two connections is going to be to community 4. So move 1 has changed, as we said. Neighbors affected by this change must return to the end of the line. So node 1 also returns to the end of the line together with node 2, right? So after this evaluation, we have this new community that 3 belongs to community 4 also, and we have 2, 3, and 4 in community 4, and 0, 1 in community 1. The next one in the line is, let's see, the node 4 evaluation. The node 4 is inside the community 4 that its only neighbor is the community 1. So if you change node 4 to community 1 and calculate the modularity, what value do we get? So after the calculations, we have the value of 0.027 that is less than 0.136 that we had before in the community with 2, 4, and 3, right? So this movement does not occur. And it stays the same configuration. So let's go to the next evaluation, that is the 2 that came back to the end of the line. So when we evaluate 2 again, 2 is going to move to the community 1 again to see if the modularity changes. So before we have here the modularity of 0.136, and moving 2 to community 1, we get the modularity of 0.069 that is less than this one. So this movement does not occur, right? If you compare to the previous community 1 modularity 2, we have the value of, let me see here, 0.1, right? That is higher than this value that we found here, moving to community 1, right? So this movement does not happen. So we keep this community here. So we go to the next step now, as the last one, that we are going to evaluate number 1, right? That's the next one in the line. And evaluating again number 1 to see if the modularity changes. So moving number 1 to community 4, we have the modularity of 0.076. So it's less than 0.1, less than the 0.136. So this is the final community configuration that we have here. So let's move on. After we have this output, let's go to step 2, that is the refinement of the partitions. In this step 2, we get the output from step 1 and evaluate again each community individually to see if we have some sub-communities inside them. In this example that we have a small number of nodes, we don't have sub-communities, but a bigger one, for example, this one, that it gets like those communities. When you do the step 1 again with each community separately, we have other results, right? After we do this again, the step 1, we have no communities. In the simple case, we have the same communities. In larger case, we can have different communities, right? After this step, we aggregate those new communities as if it was just one node. So the community detected and refined in this step previous nodes are considered as a single node. So after you consider, in this case, we have just 2 nodes, right? But in other cases, we have like 3 or 4 nodes here. This step here, you consider the weights between those nodes, the sum of the weights of the edges that previous connected the nodes between communities, right? So after that, we make moves like in the step one to see if the modularity changes, to see if the value is higher or not. And if so, we can move that sub community to that new community. But if not, you can keep the same, like move nodes and refine again. And the same steps as in step two are applied to refine the communities again and again and again. You can do it to refine your communities as much as you can. And the steps repeatedly until the modularity converge to a maximum value, as I said. And now let's explain the difference between the Louvain and Leiden algorithm. The Louvain algorithm takes the same steps as the Leiden algorithm that I explained, but the random queue execution is executed as many times as the modularity doesn't change. But in the Leiden algorithm, we just execute again the nodes that the neighbors change, as I showed before. So these two steps here happens just once. In Louvain algorithm, we repeatedly do this again and again. So this one is way faster than before, right? And in the Louvain algorithm, there's no refinement after step one. So it can lead us to some problems that when a node that serves as a bridge between two groups, for this example, and this node changes to the rest of the network, a modularity can increase, but the node that stayed here uh, can be in the same community. So if you have this situation, you're gonna have two groups that are not connecting between them, and the node that connects them is in the other community. So this makes a not really connected community, right? So when we do this refinement, you can break it into sub communities that the Louvain algorithm doesn't do that. The Leiden one does. We have better connected communities. You have a faster algorithm that will lead us to better results. And to test how well this algorithm goes comparing to the Louvain, the authors just made some tests here, and he got some database from many different sources to evaluate how the algorithm is going. After this first test, he says how badly connected communities are comparing both algorithms. After four iterations, he compares how the percentage of badly connected communities we can get based on the next iteration. So if the communities change after another iteration, the percentage of that change is a badly connected community. When we see this picture, if you look at the last iteration, the Leiden algorithm has less community that are badly connected. When you compare it to Louvain, some communities are disconnected or badly connected. Shows that the Leiden algorithm is the best one. When you see here the time of execution of every dataset, the Leiden algorithm is quite better in some cases. And when the dataset is larger, the Leiden algorithm is way faster. The other example, they made an artificial network to evaluate how both algorithms goes in time and quality. This quality is the modularity function that we just saw and the time of execution. This is the size of the network 10 to the power of 3, power of 5, and power of 7. And we have this mu coefficient that is the probability of a node falling between two communities. So if the mu is 0.2, it means that 20% of the nodes are going to be placed in the middle of two communities, and 0.8 means that 80% is going to be in the middle of two communities. So it increases the difficulty of finding communities for both algorithms. And when you see this chart, you can see that when we go higher in the difficulty and the number of nodes, the Leiden algorithm is better. It has a better quality in this case and has a lower time of execution. And in this example, we see the number of nodes 10 to the power of 7, and the most difficulty case is with zero point 0.9. We have the Leiden algorithm with way less time of execution than the Louvain algorithm. So basically, we can see that the Leiden algorithm is way faster and can bring a higher quality of the communities that are well connected. Now we are going to see the basic informations of the official algorithm. Here is this website that I'm gonna let the link in the description too. We have this introduction that says a lot about this algorithm, how to use it. We just need to import the iGraph to manipulate the graphics and the Leiden alg. And you have just to pass the T, that is your graph. From the iGraph, you get this information in this example here. And in this example, he just returns all the communities and the nodes that are inside this community. And it's really easy to use if you just can practice and read this documentation to set your project and detect the communities that you wish to. So I believe that we basically explained how this algorithm works, and this is a really good option to find communities in your network graphs. So many other algorithms can do the same thing, but I believe this one is a really interesting one that can help in many projects. So just subscribe to the channel and stay connected to see more about network graphs and computer engineering. Thank you and see you next time.